Hi. Good afternoon, everybody. So my name is Yoshinori Matsunobu. So I'm SRE at Facebook, and I also started taking a role of a MySQL technical lead at Facebook. So today I'm going to talk about database migrations at Facebook's largest, the user database, which is the main database at Facebook. So we recently migrated from a MySQL InnoDB, which is by far the most common database in MySQL, to a new database called MyRocks, which is MySQL on top of the key value store called RocksDB. So I'm going to talk about the migration stories and what issues we faced after migrations. So I'm going to talk about these topics. So first, I'm going to introduce about Facebook's MySQL and the user database. And second, I've introduced MyRocks overview, then how we migrated, and about 50% of the talk I'm going to spend about production issues, so what we faced after migrating to the production. So I think the real production case studies are more interesting for SREs, so I'm going to spend time for that. So MySQL at Facebook. So we are heavy customers of MySQL database. So right now, the latest generally available version is MySQL 5.7, but right now we are using a bit older version, MySQL 5.6. So we upgraded from 5.1 to 5.6 in about 4 years ago, and currently based on MySQL 5.6. And we have a MySQL branch called Facebook MySQL branch, which is published in GitHub. So we created many patches on top of the Oracle's official MySQL to support Facebook services. And we recently we started working pretty closely with Oracle to take our patches into official MySQL. So not only Facebook, but also the many external people can use that. And we also started evaluating and porting our patches to next major version, which is MySQL 8. So we have not used MySQL 8.0 yet, but we started porting our patches to do that. The user database, so this is by far the largest database service inside Facebook, so which stores the people's data. So like when people click likes or making comments or share stories, so these are actually stored in our MySQL database. So our MySQL database is apparently single MySQL database is not enough to serve the Facebook's workloads. So our database service is massively sharded, and users' requests normally hit in a huge cache in front of MySQL. So we have a huge cache called Tau, which runs in front of MySQL. So most read requests hit in the cache, but if cache misses, or if you write to the database, then the data is directly, the request is directly sent to the MySQL database. So if MySQL database is slow, then this affects the user's latencies. So we spend much time to make MySQL database fast enough to make people's user experience better at Facebook. And we don't run MySQL or Facebook services in the cloud. So our database is so large, so we cannot run in AWS. So we created features inside Facebook to automate most of the things, like taking backups, or if MySQL's replica is dead, then automatically replacing it. And if master is died, then automatically failing over to the MySQL slave, and automatically provisioning and reimaging the MySQL, healthy MySQL databases. So almost all operations are automated. And the last part, so this is the main topic, the reason why we migrated to MyRocks. But we are using a pure flash, PCI Express flash on database. So we used to use hard disk drive in MySQL database, but a long time ago, we switched to a pure flash. So like many other OLTP database services, So our databases are also space bound. So there are pretty good capacities for the CPUs or the IOs, but mostly it's constrained by space. So our IO and CPU are pretty idle, but we cannot put more data because it's constrained by space. So this was the major reason why we started looking into different database solutions called RocksDB. So what is MyRocks? So MyRocks is a MySQL database on top of RocksDB. So RocksDB is a key value database, which is a log structured merge key value database forked from Google's RebelDB. So RebelDB was created by Google, and which is LSM database, but it was pretty much focused on the lightweight applications. And a couple of years ago, one of our engineers at Facebook evaluated RebelDB, and it was really good. So we wanted to use it for backend databases like database. So we added several features like multi-threaded operations and several tuning options to make it work as a backend databases. And we researched the RocksDB, and which was really good to saving space because of the LSM architectures. So default MySQL database is InnoDB, which is a B-tree database. And InnoDB supports compression, but it is pretty inefficient from a space point of view. So we wanted to use RocksDB, but as several people might have experienced, have tried from migrating from a MySQL database to other key value store, like HBase or other NoSQL database, then it is really hard because the client is very different. So we wanted to migrate to RocksDB without changing application logic. So that's why we came with the idea of the MyRocks. So MyRocks is a MySQL on top of RocksDB. So MySQL has an architecture called a pluggable storage engine. So InnoDB is a storage engine of MySQL, and MyRocks, the purpose of MyRocks is creating a RocksDB as a storage engine of MySQL. By doing so, the same MySQL clients can connect to MySQL database and just switching table between InnoDB and RocksDB. So the table definition, like a create table engine called RocksDB or engine called InnoDB. Then everything is behind, it's taken care by MySQL. So users can access to InnoDB or RocksDB by the same syntax like query, SQL query, and the SQL connectors. So you don't have to change anything. So that's why we created a MyRocks database, and we tried to migrate from InnoDB to MyRocks, so without changing client logic. So this is the initial goal of the MySQL to a MyRocks migration. As I said, so InnoDB is completely space-bound in our main database. The CPU and IO utilization was pretty low, like a 20% or even lower. But the space is like using 90% of the machines. So we couldn't add more data. After our evaluations, we verified that we could save space by 50% by switching from InnoDB to MyRocks. And since we have a huge record cache, so the most read requests are hitting in the cache layers. So MyRocks, the LSM database, is a bit slower for reads, but faster for writes. But relatively reads are fewer in our main database. So we didn't increase much CPU or IO capacities, IO resources. So we could save space from 90% to 45%. By saving all of CPU and IO on the space, this means that we could add more data to the same machine. So this means the number of servers necessary to run our database services can be dropped by half. So this is a huge cost saving for us. So this was exactly what we were looking for. So after verifying that, we started carefully implementing the MyRocks to serve our services and started migrations. So MyRocks features, so MyRocks is an open source database. So you can use from several third parties like Percona or MariaDB as well. So our main goal of the MyRocks was migrating from InnoDB to MyRocks. So we created pretty much similar features as InnoDB. For example, the InnoDB uses clustered index. So we implemented the same. And to make these more efficient, so we have Bloom filters and column families to make it more efficient. So InnoDB is a transactional database, and it has a strong consistencies between the MySQL logs, like binary logs and InnoDB real log. So we implemented the same features. So we supported transactions and we supported consistencies between binlog, binary logs, and the RocksDB. And to make migrations faster, so we created several performance features like a faster data loading or deletes, and we also made replication faster. And we added many features, many options that could be changed online. Yeah, TTL is a kind of H-based features. So like after time has passed, then all the records could be automatically purged without like dropping data from a database. Run manually, you don't have to run manual delete table statement to delete all the data. And so one of the key features in InnoDB was online logical backup, like MySQL dump, or online binary copy to create a new replicas. So we are heavily using that at Facebook. So we created similar features in MyRocks as well. So there are several advantages and disadvantages in MyRocks. So these are major advantages compared to InnoDB. So the biggest one is much smaller space. So we used the InnoDB compressions, the compressed InnoDB database at Facebook. But even compared to a compressed InnoDB, the MyRocks space was about 50%, the half compared to a compressed InnoDB. So if you are using uncompressed, the regular InnoDB, after MyRocks, the space could be 20% or 25%. So you can significantly save the space. And writes are faster because LSM database is more efficient for serving writes. So faster writes means replication, the MySQL replication can be also fast as well. And bytes written to flash device is also smaller because LSM databases are more optimized database. So fewer writes means potentially so you can use more affordable flash to serving database, so which means you can save even cost even further. So MyRocks disadvantages compared to InnoDB. So the space is by far the most interesting features for MyRocks, but there are several disadvantages compared to InnoDB. So since MyRocks is newer database, so it misses several features compared to InnoDB, like foreign keys or full text index or special index support. So these are not much interesting to us at Facebook, so we didn't implement yet. But these are available in InnoDB. And so MySQL has a binary log format called statement-based and row-based. And if it's MyRocks, so you always have to use row-based binary log formats. So this is one of the limitations, actually. But we migrated to a row-based binary log a couple of years ago, so this was not a limitation for us. And more important limitation is the InnoDB is B-tree index, which are pretty balanced performance for reads and writes. So writes are faster for LSM database like RocksDB, but reads are more faster in InnoDB than RocksDB. So if your database are heavily read intensive, and if your most data fit in memory, then the InnoDB is much faster than MyRocks. In our use cases, so our database is very large, so database don't fit in memory, which is the most reads hit in the storage. The storage I/O is relatively more bottleneck, and our database is relatively write intensive because we have a huge cache. So this was not a big limitation for us. And from SRE point of view, so there are many tuning options beyond the buffer pool, like such as Linux kernel versions or file systems, the Bloom filter, or the compaction settings. So there are many options. So this may be a bit hard, make it hard for people to use MyRocks rather than InnoDB. So by accepting these limitations, we started migrating from InnoDB to MyRocks in our production database. So these are the brief overview of the technical challenges. So when migrating from InnoDB to MyRocks, the initial migration was creating a MyRocks instance without downtime, then loading into MyRocks tables within reasonable time, then verifying data consistency between InnoDB and MyRocks so that data is not broken, and then serving read and write traffics. And we also needed to continuously monitor the resource usages like space and I/O, the CPUs, or checking query plans and stores or crashes. So we monitored many metrics. The first step was creating a MyRocks instance without downtime. So in MySQL, the MySQL has a traditional the master, the primary, and the replica, the slave, master-slave replications. And all writes are going to the master, and all reads, most reads are going to be provided from our slaves. So we use a traditional MySQL single master and multi-slave architectures. So creating a one MyRocks instance was relatively easy in MySQL. So because you can just pick up one InnoDB slave, then stopping the slave, then dumping the database, then loading into MyRocks. So by doing so, MyRocks instances can replicate from InnoDB. So this was relatively easier step, but more interesting challenge was how fast we could create MyRocks instance, because you need to dump terabytes of data, then loading into MyRocks. So this is a brief overview of the normal write path in MyRocks and RocksDB. When writes coming to a RocksDB, then write request, when transaction is committed, then data is returned to a redo log called a write-ahead log. Then the same data is returned to a memory is called a mem table. Then when mem table gets full, then it's flushed, then creating a new data file called a level 0 SST file, the data files. When there are many data files, another process called a compaction happens. Then another SST files are created. And these repeats a couple of times. Then finally, the most data files are stored in the bottommost, the level max SST files. So even though you write just a couple of bytes, then same bytes are written many times, and many CPUs are also consumed. So this is pretty wasteful on the data loading, because data loading is we are doing just once. So we created a feature called fast data loading. So when the data is guaranteed by sorted by primary keys, then we can just bypassing all of the steps, then directly writing to the bottommost the data files. So by doing so, we could migrate the hundreds of gigabytes of data in just 1 hour or so. The second step was creating a second MyRocks instance without downtime. After creating first MyRocks instance, there was a InnoDB master and several InnoDB slaves and one MyRocks slave. So creating a second MyRocks instance was easier than the first step, because we can do an online copy. So you don't have to logical dump and load, just copying a binary data to a second instance. So we created a tool called a MyRocks Hot Backup, which is an online backup tool, which is also open source. So we created that tool to copy data from a single MyRocks to another MyRocks. After serving the read traffics, the next challenge is how to serve the writes in the MyRocks database. So serving writes is the most challenging part, because if we corrupt data, then it's very hard to roll back. So we created a tool called shadow testing. So MySQL has a feature called the audit plugin, which captures all reads and writes queries. After capturing the reads and writes queries, then we replayed these queries to test MyRocks instances and see if the data was fine or the queries were handled correctly or not. So we created the tool and shadowing the queries and verified the client errors or the low log contentions so that queries are they are handled properly. After these things, passing these steps, then we promoted MyRocks as a master. So from MySQL point of view, the promoting one MyRocks instance from slave to master was just a single command, the change master statement, which was very easy. But this was by far the most dangerous part. So we tested a lot to make it work. So after testing the MyRocks master, so we verified that data is consistent, and we carefully checked the number of errors on the client side. After promoting MyRocks master, then the last step was copying from all MyRocks databases to the MyRocks slaves and discarding InnoDB instances. So these were the steps we did when migrating from to InnoDB to MyRocks. So these are the basic steps to do migrations. So the more interesting stories were what issues we faced during migration and after migration. So I'm going to talk about the 4 different case studies we faced in production or during production migrations. So InnoDB versus MyRocks from my SRE point of view is there are several important differences. So most important part at Facebook was, so MyRocks was using 50% of the space compared to InnoDB, which means the servers is busier because densities get doubled. So server is busier means more performance problems may happen. So we should be prepared for having several performance issues. And the RocksDB is much newer database compared to InnoDB. So InnoDB has 20 years of histories, but RocksDB has only a couple of years of history. So RocksDB is newer database that changed rapidly, which means it's expected to several bugs when even after deploying production. And from a architecture point of view, so MyRocks and RocksDB relies on the buffered I/O and the Linux kernel, while InnoDB uses direct I/O. So this means the RocksDB more heavily dependent on the Linux kernel. So if you have issues in the Linux kernel, so RocksDB will have more issues compared to InnoDB. And from other architecture point of view, so for large transactions, the commit needs more work than InnoDB. So because all changes are kept in memory in current RocksDB and MyRocks, and everything is written to a RocksDB mem table memory structures at commit. So commit needs more work compared to InnoDB. And there are many tuning options beyond buffer pool. So this may be a bit hard for properly tune. And faster writes means replication slaves lag less often. So this is relatively good news for MyRocks. So this the first case was stored on commit. So after testing MyRocks on masters, so every few minutes, so on busy servers, so we started observing the commits taking 100 milliseconds or even a few seconds. So how we found this? So MySQL has a couple of commands like show global status to check how many threads are actively running, and show process list to print the running queries. We saw that many MySQL clients are waiting for commit statements. So this was pretty weird for us. So we started investigations. So when checked machines, the CPU and I/O and flash devices were not busy. So the cause was somewhere else. So we carefully looked at several metrics, and we have a tool called atop. So every few seconds, capturing the top and archiving that. And when I checked on exactly the time the store happened, then the memory store also happened. So this suggested that hitting a stores on memory allocation. So this was the exact issues that caused the commit stores. So the RocksDB, as I said before, so RocksDB has very limited support for direct I/O. So we are using the buffered I/O in MyRocks, so while we used direct I/O in InnoDB. So the commit path involves lots of memory operations like a mem table writes, a binary log, a write log writes. So there are lots of memory operations which caused the kernel memory allocation stores. So this was the cause of the memory allocation, the commit stores in MyRocks. So we discussed with the Linux kernel team at Facebook. So we upgraded our Linux kernel from older one, the 4.0 to 4.6, the latest kernel, so which fixed the most of the memory allocation stores. And we also changed several data loading queries, like schema changes, to MyRocks bulk loading, so that we don't have to write the mem table. After these steps, then commit stores every few minutes, then these dropped to nearly 0, so we could finally fix the problem. The second issue was the application bug. So the few deleted records that reappeared. So some of the secondary indexes started to have extra records on very few instances. So we started seeing the problem. So after several debugs, so it turned out to be a bug in RocksDB's process called compactions, that in rare cases, on heavy deletions, then deleted records might have not been handled correctly. So this was one of the bugs we faced in production. So how did we find the bug? So we continuously ran the data correctness checks, comparing counts and checksums between primary key and secondary keys. And we started seeing the mismatches between the primary key and secondary keys on a very few, 1 or 2, the MySQL instances. So after seeing the issues, the next step is finding a root cause. So why this problem happened, so how we can mitigate the issues. So we drained the affected MySQL instances for investigations and identified when the issue happened, the found last update timestamps from the MySQL column, and searched the SST files, data files that contained the keys, and looked into a RocksDB log. RocksDB has a log file, of course, and looked in logs and how these files are created. After getting these informations, so worked with the RocksDB engineering team at Facebook to figure out the possible causes and relevant diffs. So we investigated the diffs relevant to the diff problems, and we finally found that the new feature in the RocksDB's new feature called level 0 to level 0 compactions caused the problem. So after finding the root cause, then we fixed the problem. We could fix the problem. So easy way to check index consistencies in MySQL is run a union statement. So select count from a fourth index primary key, and the union the select index count from a different index, then comparing the records. Then this was one of the easiest steps to finding the mismatches. Yeah. The third case is another weird issue was the counting from one of the empty table started taking a few minutes. So this scared us a lot. So one of our production instances started having these issues. So hopefully the only one instance got affected by the issue, but this scared us a lot because if many instances hit these issues, then we cannot serve user request. So we started draining the instance and trying to reproduce how this problem might happen. So try to reproduce. So we verified that this issue didn't happen with insert, and this issue didn't reproduce when selecting records with primary key lookups, and sometimes reproduced with range scans and sort ordering, like order by ascending or descending, the matters the results. And RocksDB has an internal feature called Bloom filters, and the Bloom filter also mattered. So after the testing of various scenarios, we categorized like this. So when Bloom filter was used and using ascending scan, then we didn't hit the issues. Otherwise, then we hit the issues. So after narrowing down the potential causes, then we investigated the instance with RocksDB teams. So we debugged with the reproducible test cases. And finally, we concluded that there were 4 different bugs. So when you heavily delete the database tables, and if you run the long-running transactions like backups, online backups, then delete markers in RocksDB, which is called tombstones, might not be deleted, and it remained in the bottommost the data files. And and also we missed the proper boundary checks for descending scans with Bloom filter was used. Or we also missed several boundary checks in RocksDB and MyRocks. After finding these issues, then we could finally fix the problem. The final issue was trying to write core files, then crashed Linux machines. So MyRocks is a new database, so we expected the MySQL database crashes often. So we tried to enable core file when MySQL is crashed. Then we wanted to investigate the root causes of the core file, the crashes. But after enabling core files for MySQL process, then we started observing more host reboots, so unplanned kernel crashes than before. So originally we didn't know that it was because of the core file. So we first investigated the cause of the host reboots. So first checked the MySQL error logs. So MySQL error logs shows that it tried to write the core files before kernel crash. But core files were not actually written. And the ATOP shows that the virtual memory in MySQL process was extremely large, like hundreds of gigabytes. And our default core file dump location was a root function, which was ext4 file system, and which was smaller than the MySQL, the virtual memory size. So the large virtual memory size is actually causing problems when writing a core file. So our MyRocks and RocksDB built with jemalloc, the memory allocator, takes very large virtual memories, the BART. So growing RSS, the residential memory, is a memory leak, but the large virtual memory is fine. So it's not a memory leak. But large virtual memory is annoying when writing a core file. So when writing a core file, it needs to, on the Linux side, it needs to allocate the space that it calculated extents based on the hundreds of gigabytes of the virtual memory. And since there was no space on the root functions, it couldn't pass the calculations, and finally the Linux kernel crashed and rebooted. So we disabled core file from my.cnf in the MySQL, and we tried to print stack traces by pstack before aborting MySQL. So what we wanted the most was the stack traces. So the core, it's pretty cool that you have a core file, but even stack traces was pretty useful. And we are also working in progress to compress core files prior to dump, so that we like running a GSTD prior to writing a core file, so that core files could be compressed to a few gigabytes, so that we could write. Yeah, so these are major lessons we after we faced after migrating from InnoDB to MyRocks. So we learned lots of lessons, but I think that these two are the most important for us. So first one was learn how core components like Linux or RocksDB work. So people may use the databases as a black box, but once you have issues, then the deep understandings about the underlying database like RocksDB or MySQL or InnoDB or Linux will hugely helpful. And do not ignore outliers. So actually, we have many databases. I'm not allowed to say the exact numbers, but we have many databases, and we hit issues only a few databases. So if we check only P99 or average, then we could not find the issues. Then after affecting, so then the bugs might be left behind for a couple of months. Then after that, more serious issues might have happened. So do not ignore outliers, and many of and check the outliers, and then take actions as quickly as possible. So after these lessons, so our current production status is, so we completed the InnoDB to MyRocks migration in our main users database. So we could save space by 50% in UDB compared to a complex InnoDB. And we started the migrating on other database tiers. So user database, UDB, is by far the largest database at Facebook, but there are several other databases in Facebook. So we started migrating them. So hopefully I can share more interesting stories after that. Thank you. That's all. So I have about 4 minutes for questions. So if you have anything, then come to the mic.
So you mentioned that you compared the data between InnoDB and the MyRocks after you had done the migration. Could you talk a little more about how you did that comparison?
Yeah, the question was we compared between the InnoDB and MyRocks to different databases. So the MySQL has a feature called a global transaction ID, GTID. So GTID is the UID that specifies that distinguishes the transactions consistencies. So what we did was stopping MySQL replications with the same GTID, then started transactions, then after that starting replication. After that, the running a select statements and compare these two. Since InnoDB and the MyRocks started with the same GTID, so the result has to be consistent. This is what we did to compare InnoDB and MyRocks. Yes.
Why did you do the biggest DB first?
The biggest DB?
You said the USEDB is the biggest one, but yes, you're doing the smaller ones later. Why didn't you start with the smaller one and work your way up?
Okay, the question was why we started migration with the biggest one. So actually, we have a test database, which is very small. So the first customer was a test database, so which has only a couple of databases. So this was the first. So the UDB was the second one. Does it answer your question? So we try to mitigate the risks. Any other questions? Okay, I'll be in the Facebook booth for a while. So if you have any questions, feel free to visit and ask me. Thank you very much.